Welcome to the Layer 2 Connectivity over a Layer 3 Network module. By the end of this module, you should be able to explain Layer 2 connectivity over a Layer 3 network.
Data centers host different types of applications. There are a few ways for applications to function. A Mode 1 application requires a direct Layer 2 connectivity between the different devices that host the applications. A Mode 2 application does not require Layer 2 connectivity, but can run on a Layer 3 network using an IP reachability instead of Layer 2 reachability between application nodes. As data centers have grown, and application mobility and the need to move applications from device to device within the data center have become increasingly common, the limits of Layer 2 only data centers have become more apparent. Building a Layer 2 data center, which is based on VLANs, and the manual mapping of broadcast domains to accommodate the needs of legacy applications can be cumbersome from a management perspective. It is often not agile enough or scalable enough to meet the demands of modern business needs.
To address the scalability and agility needs of modern businesses and applications, new methods of designing and building data centers have been established. Instead of using a Layer 2 switch network between host devices, the concept of an IP-based fabric has been introduced. Using an IP fabric within the data center enables the use of routing protocols to interconnect edge devices and enables the use of the scalability and load-sharing capabilities that are inherently built into the routing protocols. Using a Layer 3 network between edge devices introduces a problem with legacy applications. Many legacy applications, or Mode 1 applications, still require direct Layer 2 connectivity between hosts or application instances. Placing a Layer 3 fabric in between Layer 2 broadcast domains disrupts the Layer 2 connectivity. Layer 2 virtual private networks, or VPNs, address the need to stretch a Layer 2 domain across a Layer 3 domain. The foundation of this Layer 2 stretch concept is based on the functionality of a standard Layer 2 VPN, or L2 VPN. With an L2 VPN, a data frame is encapsulated within an IP packet at the boundary of a Layer 2 broadcast domain and an IP routed domain. The encapsulated packet is routed across the IP domain and is then decapsulated once it reaches the Layer 2 broadcast domain at the remote side of the Layer 3 routed domain. From the perspective of the hosts, at each end of the network, they are still connected with a direct Layer 2 connection. The encapsulation and decapsulation used to cross the IP fabric is transparent. From the perspective of host B in the example shown, host A is directly connected to the same broadcast domain as host B, and they can communicate directly across that Layer 2 domain. There are generally two components of a VPN, the data plane and the control plane. The data plane of a VPN describes the method in which a gateway encapsulates and decapsulates the original data. Also, in regard to an Ethernet Layer 2 VPN, it might be necessary for the gateway to learn the MAC addresses of both local and remote servers, much like how a normal Ethernet switch learns MAC addresses. In almost all forms of Ethernet VPNs or EVPNs, the gateways learn the MAC addresses of locally attached servers in the data plane from received Ethernet frames. Remote MAC addresses can be learned either in the data plane after decapsulating the data received from the remote gateways or through the control plane. The control plane describes the process of learning performed by the VPN gateways. This includes learning the remote IP address of other VPN gateways, establishing the tunnels that interconnect the gateways, and sometimes learning the MAC addresses of the remote hosts. The control plane information can be statically configured or dynamically discovered through some type of dynamic VPN signaling protocol. Static configuration works fine, but it does not scale well. For example, imagine that you have 20 top-of-rack or Tor routers participating in a statically configured Layer 2 VPN. If you add another top-of-rack router to the VPN, you have to manually configure each of the 20 routers to identify the newly added gateway on the VPN. In addition, imagine that the workloads, or applications running in the network, are constantly being moved from one physical host to another. Adjustments to the constantly moving workloads is difficult, if not impossible, to achieve. Normally, a VPN has some form of dynamic signaling protocol for the control plane. The signaling protocol can allow for dynamic additions and deletions of gateways from the VPN. Some signaling protocols also allow a gateway to advertise its locally learned MAC addresses to remote gateways. Usually, a gateway has to receive an Ethernet frame from a remote host before it can learn the host's MAC address. Learning remote MAC addresses in the control plane allows the MAC tables of all gateways to be more in sync. This has a positive side effect of causing the forwarding behavior of the VPN to be more efficient, that is less flooding of data over the fabric. Different types of Layer 2 VPN technologies exist. Some of these technologies were developed for and are most beneficial in a WAN environment. They are not suitable for data center environments. Some examples are Circuit Cross Connect, BGP Layer 2 VPNs, LDP signaled Layer 2 circuits, or Virtual Private LAN Services or VPLS. These are often services that are provided by the service providers to connect corporate sites across WAN connections. However, these technologies are not optimized for data center environments where applications and workloads can frequently move, and physical and virtual hosts can number in the thousands or tens of thousands. Two options that have been developed for a data center environment and which work together to provide flexibility and scalability are Ethernet VPN or EVPN and Virtual Extensible LAN or VXLAN. These are two separate technologies that can work together to manage both the forwarding and control planes in a data center. Refer to the Juniper Pathfinder website for the current list of devices that support EVPN and VXLAN. You can access the website from the reference links document. Note that if a device is using EVPN-VXLAN, then it does not use Virtual Chassis Fabric or VCF, Virtual Chassis or VC, or Multi-Chassis Lag or MC Lag. VXLAN was developed as a Layer 2 encapsulation protocol. VXLAN encapsulates a Layer 2 frame in a Layer 3 IP packet. It inserts identifiers within the packet header to label and identify to which broadcast domain an encapsulated packet belongs. This is similar to how a VLAN tag identifies a broadcast domain in a VLAN switched network. The Virtual Network Identifier, or VNI, identifies a broadcast domain by using a numeric value. Unlike a VLAN tag, which can be in the range from 0 through 4095 12-bit value, the VNI value can range from 0 through 16,777,215 24-bit value. A packet with a VNI tag in the header can be associated with any one of these 16 plus million broadcast domains. This alleviates a significant scaling limit associated with VLANs. It is recommended to use a VNI that starts with a value of 5,000 or higher to avoid confusing a VNI value with a VLAN tag value. In a data center, a VLAN is mapped to a VNI value. However, when the packet enters the Layer 3 domain and is encapsulated in a VXLAN packet, the VLAN ID is discarded and is not transmitted with the original packet. Once the packet arrives at the remote gateway, the VLAN ID associated with the VNI at the remote gateway may be placed on the packet before it re-enters the Layer 2 domain.
The process of encapsulating, decapsulating, tagging, and forwarding VXLAN traffic in a network corresponds to the data plane. For a local VXLAN gateway to identify which remote VXLAN gateway should receive an encapsulated packet, the local gateway must learn where the remote gateways are and what MAC addresses and broadcast domains are reachable through those remote gateways. The process of learning where remote destinations are and how to reach them corresponds to the control plane. The VXLAN control plane has gone through some changes in evolution. Originally, VXLAN gateways learned about remote destinations through multicast. Although this control plane function worked, it was very resource intensive, was slow to converge and to update when changes were made, and required the running of a multicast protocol in the underlay network. It also required manual configuration on every gateway to associate locally connected broadcast domains with multicast group addresses. To improve performance of the VXLAN control plane, EVPN was developed. EVPN signaling is an extension to the BGP routing protocol. EVPN signaling utilizes BGP routing updates to advertise local broadcast domains and locally learned MAC addresses to remote tunnel endpoints. The BGP routing protocol was designed for high scalability, fast convergence, and flexibility.
Benefits of VXLAN are as follows. VXLAN is being embraced by major vendors and supporters of virtualization. It is a standardized protocol and has the support in many virtual switch software implementations. Deploying an EVPN-VXLAN framework provides the following benefits. Programmability allows you to easily automate. Its open standards-based architecture ensures backward and forward interoperability, integrated and efficient Layer 2 and Layer 3 connectivity with control plane-based learning, easy network scalability that's based on business needs. Network segmentation inside and across multiple campuses and data centers allows you to securely separate traffic. Minimized fault domain increases reliability of your network. MAC address mobility provides flexible yet simple deployment capabilities. Loop-free technology mitigates the need for spanning tree protocol, or STP, and active-active redundant links, fully utilizing network bandwidth. With the introduction of virtualization within a data center, the manner in which applications and physical hardware interact has changed drastically. This change has brought about new networking requirements. Virtual machines, or VMs, or software-based computers that run an operating system and applications and can be run on an underlying physical host. A single physical host machine can be host to numerous virtual machines. The ability to move a virtual machine to any physical host within the data center enables a more efficient use of resources. If the resources of a physical host become taxed due to increased memory or CPU requirements of the virtual machine or applications, a portion or all the processes of that virtual machine can be migrated to a different physical host that has sufficient resources to support the virtual machine requirements. Physical resources within the data center can be monitored and analyzed to track historical resource usage, as well as predict future resource requirements within the environment. Because the workloads are software-based, automated systems can be used to migrate workloads with little to no user intervention. The ability to move workloads to the physical resources that can most efficiently handle those workloads introduces a new set of issues with regard to the network that interconnects the workloads. As a workload migrates to a new physical or logical server, other applications or hosts within the data center environment must be able to continue to communicate with the migrated resource, regardless of where the resource exists. This can, at times, involve a change of physical server, change of rack, and at times even a change of data center locations. In addition, the original MAC address of the virtual or physical machine on which the application is running changes, and the mechanisms used to interconnect the devices at a Layer 2 level must be able to adapt to an ever-changing environment. VXLAN module. By the end of this module, you should be able to describe VXLAN fundamentals. VXLAN is defined in RFC 7348. VXLAN, a framework for overlaying virtualized Layer 2 networks over Layer 3 networks, and describes a method of tunneling Ethernet frames over an IP network. RFC 7348 describes the data plane and a signaling plane for VXLAN. Although RFC 7348 supports protocol-independent multicast or PIM and multicast in the signaling plane, methods for VXLAN exist, including multi-protocol BGP or MPBGP, Ethernet VPN or EVPN, as well as Open vSwitch Database or OVSDB. Refer to the Juniper Pathfinder website for the current list of devices that support VXLAN. You can access the website from the reference links document.